Jennifer Pulley, and welcome to NASA Connect, the show that connects you to the world of math, science, technology, and NASA. Today, we're at NASA Glenn Research Center in Cleveland, Ohio, and this is the Zero Gravity Facility, and it's where NASA conducts microgravity experiments. You've seen microgravity. You've seen it in videos of the International Space Station and on NASA's KC-135. On today's program, we'll investigate how NASA researchers conduct research in a microgravity environment. You'll observe NASA researchers using the math concepts of measurement, ratios, and graphing to research combustion science, and the importance of fire safety on the International Space Station. In your classroom, you'll do a cool hands-on activity to learn more about gravity by collecting, organizing, graphing, and analyzing data. And using the instructional technology activity, you will investigate apparent weight to see how astronauts in space can feel weightless. NASA researchers use the math concepts of ratios, measurement, and graphing all the time. First, let's review ratios. A ratio is a comparison of two quantities. For example, NASA Glenn Research Center and NASA Marshall Space Flight Center, which are the NASA facilities that primarily conduct microgravity research, are 2 of 10 NASA centers located across the country. A ratio can be written as a fraction, and it can be written in any form that is equal or equivalent to that fraction. So the ratio 2/10 can also be written as 2:10, 20%, 20/100th, and 0.20. When you work with ratios, you can express fractions, decimals, and percentages. To learn how NASA researchers apply the concept of ratios to the microgravity environment, let's go see Dr. Roger Crouch. He's the senior scientist for the International Space Station. Hey, Dr. Crouch.
Hello, Jennifer. Math is very important to everyone, but especially to scientists and engineers. We use ratios in every aspect of research in a microgravity environment.
So, Dr. Crouch, what is microgravity?
Microgravity is a condition where the effects of gravity are, or appear to be, very much smaller than they normally are here on Earth. The prefix micro comes from the Greek root mikros, which simply means small. However, in the scientific metric system, micro literally means 1 part in a million, or 1 to 1 million. We use the term microgravity to describe the environment on board a spacecraft in orbit around the Earth. Gravity is everywhere. We usually call it high gravity if it's more than here on Earth, and low gravity if it's less than here on Earth. An example of a low gravity environment would be the Moon. The gravity on the Moon is about 1/6 of that here on Earth.
Hey, 1/6, that's a ratio.
That's right. What are the quantities being compared in this statement? The gravity of the Moon is about 1/6 that on Earth. If you said the Moon's gravity to the Earth's gravity, then you're starting to understand ratios. The ratio 1/6 means that the gravity of the Moon is 6 times smaller than the gravity on Earth. We sometimes use the term microgravity to describe a condition where gravity is not small, but appears to be small. This is a condition experienced on orbiting spacecraft such as the International Space Station, or ISS, the Space Shuttle, and all objects in free fall. That's me appearing to float inside the Space Shuttle. Really, I'm not floating, but falling at the same rate as a shuttle. So to the observer, it looks like I'm floating.
So microgravity is not really zero gravity.
That's right. It diminishes relatively quickly with distance, so it's weaker on the space station than it is on Earth. But it's 6,400 kilometers from the surface to the center of the Earth, which is considered the origin of the Earth's gravity field. Then the ISS is only another 400 kilometers above the surface of the Earth. So at that altitude, the gravitational acceleration is still about 89%, or 89/100ths, of that of the Earth's surface. If the gravitational acceleration on the surface of the Earth is 9.8 meters per second squared, what would the gravitational acceleration be 400 kilometers above the surface of the Earth?
Let's see. You would approximate the gravitational acceleration at 400 kilometers above the Earth's surface by calculating the product of 9.8 and 0.89, or 89/100.
That's correct. By multiplying 9.8 and 0.89, we see that the gravitational acceleration at 400 kilometers above the Earth's surface is about 8.7 meters per second squared. Comparing 9.8 and 8.7 meters per second squared, gravity at the altitude of the ISS is nearly the same as that on Earth. But given the images of floating astronauts, it appears that gravity is reduced by much more than 11%.
So, Dr. Crouch, what is happening here?
Gravity attracts all objects towards the center of the Earth at the same rate. If I release two objects of different weight and they have room to fall, they will accelerate towards the center of the Earth at the same rate until they meet the resistance in the form of the floor, for instance. In other words, they'll hit the floor at the same time. It's the force of the floor that we feel is our weight. When gravity is the only force acting on an object, then it is said to be in a state called free fall. Objects in free fall can be said to be weightless. Imagine you have an apple on a scale which displays the apple's weight. If you drop the scale, the apple and the scale will fall together, but the apple will no longer compress the scale, so the scale will show zero weight. In the same way, astronauts inside the ISS or the space shuttle are falling around the Earth. Unlike the apple on the scale, both the astronauts and the spacecraft free fall by circling the Earth at approximately 7,870 meters per second or 17,000 miles per hour. They're falling towards the Earth, they just never get there.
How are the concepts of measurement and graphing important to NASA researchers and scientists?
Research in the space environment gives scientists a new tool for looking at phenomena in ways that is just not possible here on Earth. But these discoveries won't take place without understanding and applying the math concepts of measurement and graphing. To demonstrate how scientists and researchers use these concepts, Dr. Sandra Olson, a microgravity combustion scientist at the NASA Glenn Research Center, will tell us more.
Oh, great. Thank you so much, Dr. Crouch.
Thank you, Jennifer. I enjoyed it.
Now, before we visit Dr. Olson, let's review the math concepts of measurement and graphing. Measurement. It usually tells us the size of something and consists of a number and a unit. For example, the gravitational acceleration at the surface of the Earth is 9.8 meters per second squared. 9.8 is the number, and meters per second squared is the unit. The unit in a measurement is a fixed quantity with a size that is understood. The number in a measurement tells how many units there are in what is being measured. This allows us to compare the size of what's being measured to the size of the unit. For example, Dr. Crouch indicated that the gravitational acceleration 400 kilometers above the Earth's surface is 8.7 meters per second squared units, compared to the gravitational acceleration at the Earth's surface, which is 9.8 meters per second squared units. Notice that the unit of measurement is the same for both numbers. And in case you're wondering, what does the unit meters per second squared mean? Well, 1 meter per second squared, or 1 meter per second, means that for every second of travel, the velocity increases by 1 meter per second. So, if the acceleration due to gravity is 9.8 meters per second squared, then for every second of travel, the velocity increases by 9.8 meters per second. Okay, guys, the next math concept for today's show is graphing. And graphing is really important because it creates a visual representation of relationships that may not be easily determined using numbers alone. And there are many different types of graphs that can be used to visually represent data. There are bar graphs, circle graphs, line graphs, pictographs, and scatter plots, just to name a few. Remember when Dr. Crouch told us that gravity diminishes as we get farther and farther away from the Earth? We can represent this visually with a graph. The x-axis, or horizontal axis, represents distance, and the y-axis, or vertical axis, represents gravity. From the graph, you can see that gravity decreases with increasing distance. So, are you with me so far? Good. Let's go chat with Dr. Sandra Olson here at NASA Glenn Research Center.
How do fires in space travel differently from fires on Earth?
From the position versus time graph, what type of relationship exists from the flamelets?
What does the slope of a position versus time graph tell you?
Hey, Dr. Olson.
Hello, Jennifer. I'm glad you were able to come to see our facility today. Thank you for asking me to explain how we use measurement and graphing techniques in our research.
So what kind of research do you do here?
I do experiments in microgravity combustion, especially as it relates to spacecraft fire safety. You know, Jennifer, we're told as children that if there's a fire in our house, we're supposed to get out of the house and call the fire department. But in spacecraft, this isn't an option. There are no fire departments in space, and you just can't walk outside. A bad fire actually happened on the Russian Mir space station in 1997. We need to understand fire behavior in microgravity so that we will know how to avoid the fire as much as possible and survive it if it does occur.
Now, Dr. Olson, it sounds to me like you're saying that fire behaves differently in space than it does here on Earth.
Very differently, Jennifer. Gravity is such a dominant force in fires here on Earth that we take it for granted. For example, a wildfire is very gravity dependent. On Earth, wildfires spread uphill much faster than downhill. The reason for this is that the heated air from the fire rises up the hill and heats the fuel, like the grass, trees, and shrubs, ahead of the fire. Blown into the wind, the fire's reach is long, and it can spread very fast over the nice warm fuel. On the other hand, going downhill, the wind is fresh, cool air being drawn into the fire to replace the rising hot gases. The vegetation remains cool until the flames are very close. The flame's reach is very short, and it takes longer to heat up the cold fuel, and the flame spreads more slowly. In space, fires like to go in the exact opposite direction. They like to spread against the wind, while wildfires are blown by the wind. Because hot air doesn't rise in a microgravity environment, the only airflows in an orbiting spacecraft come from ventilation fans, cooling fans, and crew movements. A fire, given a choice in this microgravity environment, will preferentially spread into the fresh air. The flame doesn't have any control over the airflow, so it has to seek out the fresh air. The wind-blown or downwind side of the flame is only receiving polluted air that contains smoke and carbon dioxide, but not much oxygen, because that's already been consumed by the upwind side of the flame. So when the air flows from the ventilation fans are low, the downwind side of the flame can't spread at all. Even though it has fuel and heat, it doesn't have the oxygen. In a microgravity environment, if we reduce the airflow, even the oxygen-seeking upwind side of the flame has trouble getting enough oxygen, and it breaks up into little flamelets.
Okay, so how do you measure or collect data on these little flamelets?
In our experiments, we use this droppable wind tunnel to study the effect of airflow on the flamelets. When we drop this miniature wind tunnel, we can get brief periods of microgravity here on Earth. We can measure the effect of airflow on the flame by applying a very low-speed airflow to a flame as it spreads across a thin sheet of paper. As it spreads, we can measure its position as a function of time and plot time and position on a graph. The following graph allows us to compare position versus time for flamelet tracking. The x-axis, or horizontal axis, is the time measured in seconds, and the y-axis, or vertical axis, is the position of the flame measured in millimeters. This graph represents a flame that starts out uniform and after 5 seconds of travel breaks up into flamelets. The point 00 represents the location where the uniform flame breaks up into flamelets.
Okay, Dr. Olson, from this graph, there appears to be a linear relationship between position and time. Why is the slope of the line representing the uniform flame steeper than the line representing the flamelets?
That's a great question, Jennifer. The steepness or slope of the line tells us the spread rate or the velocity of the flame.
So let me see if I get this. As the slope of the line decreases, then the spread rate or velocity decreases.
That's correct. For this particular test run, the velocity of the uniform flame was calculated to be 3.4 millimeters per second, and the velocity of the flamelets was calculated to be 1.0 millimeters per second. Although the flamelets spread more slowly, they're very hard to detect. And they can flare up into a big fire again if we turn up the airflow. Imagine if the astronauts put out a fire and then turned on the air circulation system to clean up the smoke. The fire could flare up again.
Wow, I can see how important your research is to the safety of the astronauts on board the International Space Station and the Space Shuttle. Thank you so much, Dr. Olson.
Thank you, Jennifer.
Hey kids, it's now time for a cue card review.
How do fires in space travel differently from fires on Earth?
From the position versus time graph, what type of relationship exists from the flamelets?
What does the slope of a position versus time graph tell you?
Okay, let's review. We highlighted the math concepts of ratios, measurement, and graphing. Dr. Crouch applied the concept of ratios to help us define microgravity. And Dr. Olson explained the importance of measurement and graphing while conducting spacecraft fire safety research. Now it's your turn to apply these math concepts in your classroom. Check out this program's awesome hands-on activity.
Hi, we're students at Northside Middle School, here in Norfolk, Virginia.
NASA Connect asked us to show you this program's hands-on activity.
You can download a lesson guide and a list of materials from the NASA Connect website.
Here are the main objectives. Students will apply techniques to determine measurements, use metric measurement, Build mathematical knowledge through investigation and experimentation. Collect, organize, and graph data for analysis. Build an understanding of microgravity.
Good morning, class. Today, NASA has asked us to investigate how graphing techniques are helpful in understanding the concepts of position, velocity, and acceleration.
Teachers will find a location for dropping pre-selected objects. A set of bleachers provides a good variation in heights without using ladders. Mark the drop location in even increments, if possible. 8 to 10 drop stations create a good graph that students can easily view. Measure each station in meters or inches and use the conversion 1 meter equals 3.281 feet. Organize students into groups of 4. Once each group has selected a different ball to use for all their test drops, distribute the student materials. A student recorder writes down the height of each drop station on the data collection chart. A student timer records 5 drops at each drop station. Only the ball dropper should climb to the drop site, with the rest remaining at ground level. The student counter returns the ball to the dropper and begins the countdown again when everyone is ready. Average the times for each drop station and record on the data collection chart. Square the average times for each drop station and record on the data collection chart. Using height and average time data for each drop station, plot a distance versus time graph on drop data chart 1. Using height and average squared time data for each drop station, plot a distance versus time squared graph on drop data chart 2. The teacher will collect the drop data charts from each group and compare the data on drop data chart 1 for each ball and discuss the shape the data points create. Next, overlay all drop data chart 1 transparencies to compare the data simultaneously. In the next comparison, compare the data on drop data chart 2 for each ball and discuss the shape the data points create. Again, overlay all drop data chart 2 transparencies to compare the data simultaneously.
It's time for questions. Based on your observations, predict what will happen to the acceleration if the object is dropped from a greater height. Christine.
I don't think it'll matter where you drop the ball from the bleachers, the acceleration will stay the same.
Great answer. Mr. Coppola?
Thank you. Did the shape or surface of the object dropped have any effect on the results? Explain. John?
I don't think that it would have any effect on this experiment because we're using an object such as a ball, and the air resistance is negligible. But on the other hand, if we were to use an object such as a piece of paper, it would float down and take longer to hit the ground.
Teachers, if you would like help to perform the preceding lesson or any other NASA Connect lesson, simply enlist the help of an AIAA mentor who will be glad to assist your class in these activities.
Super job, you guys! Hey, did you know that NASA is working with students to develop new products and new experiments for space research? Dr. John Poyman, a professor of chemistry and biochemistry at the University of Southern Mississippi, has some cool applications for microgravity research, which students just like you can be working on someday.
What is buoyancy-induced convection?
What is the relationship between density and volume?
What is the trend in the density versus temperature graph?
Hi. NASA's Reduced Gravity program began in 1959, but in the past 5 years, students from over 100 schools have performed experiments in a microgravity environment. Several of my students and I have flown on the KC-135, NASA's flying laboratory. It's science that's interesting, challenging, and fun. One experiment we are conducting involves making new space-age materials by a really cool process called frontal polymerization, and the other involves studying how molecules attract each other in fluids that mix. Everything is made up of very, very small pieces of stuff called molecules. Molecules attract each other. How strongly they attract determines if the stuff is a liquid, solid, or a gas. Some materials mix completely, others do not. Here's something you can try at home yourself. We have water here, which has food coloring in it, and syrup. And as I pour the syrup in and stir it up, it'll make one continuous liquid. But if I take something that's immiscible with water, like mineral oil, and pour it into the water with food coloring, and mix this solution up, it will separate into 2 layers with time. Water molecules attract each other more strongly than they attract oil molecules, and so the water stays separate. A monomer is a small molecule that can be made to form long chains of monomers connected end to end, called a polymer. It's sort of like boxcars hooked together to form a train. The mixing process is called convection. It's the term for liquid motion. There are two ways in which convection can spontaneously occur in a liquid. One is caused by gravity and is called buoyancy-induced convection. Differences between the densities of the liquids make the lighter fluid rise and separate from the heavier fluid. Another type of convection is called interfacial tension-induced convection.
Interfacial what?
Interfacial tension-induced convection. Let's split the term up. First, interfacial tension is like the surface tension, which holds up a water bug when it skitters across a pond. The surface is the result of the water molecules attracting each other. But heating a surface here on Earth causes buoyancy-induced convection. How can we study only the convection caused by interfacial effects alone? We need to eliminate gravity or its effects. We can never eliminate gravity, but by free-falling we can create a system that acts as if there were no gravity. Performing experiments in weightlessness allows us to study phenomena we can't study on Earth, and to answer questions we can't answer down here. By eliminating buoyancy-induced convection, we sometimes can create superior protein crystals in weightlessness that can help researchers design new drugs. Eliminating buoyancy-induced convection can also help us understand how to make better semiconductors here on Earth, like the ones used in your computer. We take a lesson from computer chip manufacturers who use light to make the circuit patterns. Microgravity research shows us that we can create patterns on fluids which would not be allowed on Earth, where buoyancy convection mixes up the patterns due to gravity. My students and I are studying how forces between molecules in fluids that mix can cause convection. We use light as an initiating agent to make the monomer turn into the polymer. By exposing the monomer to light with a specific pattern, we hope to observe how the monomer and polymer molecules pull on each other. For many minutes, we predict that the two fluids will act like oil on water. But in the long run, the molecules will diffuse into each other and make a single fluid. Why can't we do the experiment in the lab? Because buoyancy-driven convection will smear everything out. So there really is no way on Earth to do the experiment. We also study a process called frontal polymerization, in which plastics and foams can be made with a chemical reaction that spreads out like a liquid flame. Gases can be released by the hot reaction that makes bubbles, which can form the foam. Of course, bubbles float in a liquid because of gravity. But without the buoyant force, bubbles can become larger in a microgravity environment.
How do you use math in your work?
Math is essential to our work. For example, in order to predict how gravity will cause convection in our systems, we need to prepare graphs of the density of our materials as a function of temperature. We use a special instrument called a densitometer. But we have to know how to use the math to make sense of what it tells us. Let's look at some of the data from my lab. Here we have plotted the densities of the monomer and the polymer on the y-axis and the temperature on the x-axis. First, notice that the density of the polymer is higher than the monomer. Next, we can draw straight lines through the points. The slope of each line is the ratio of the change in density to the change in temperature. The density of the polymer decreases 0.03 grams per cubic centimeters for a 50 degrees centigrade increase in temperature. The density of the monomer also decreases, but it decreases 0.04 grams per cubic centimeter for the same temperature change. Remember that we said buoyancy-driven convection happens because of differences in density, and that the less dense liquids will float to the top. And information from this graph tells us how the density changes when we heat the monomer and polymer, and so we can predict how much buoyancy-driven convection will occur during experiments on Earth. The graph also tells us how much the volume changes as we heat the liquids, essential information for designing our experiment on the International Space Station. As we go farther and farther from Earth into space, we're going to be required eventually to make our own materials in space. Foams are just one of the things we need to look at. Gaining an understanding of the opportunities in microgravity research today will be valuable knowledge for you, the young researchers of tomorrow, when we are ready for our first manned flight to Mars.
All right, guys, it's now time for a cue card review.
What is buoyancy-induced convection?
What is the relationship between density and volume?
What is the trend in the density versus temperature graph?
Okay, did you get all that? Let's go visit Dan Giroux in his web domain.
Hi, and welcome to my domain. NASA Connect has created a really cool web activity to help you understand apparent weight. and to see how astronauts in outer space feel weightless. We also have a second activity to help you make an important elevator design decision. First, be sure you have the Squeak plugin. It can be downloaded at www.squeakland.org for easy installation. Once you have the Squeak plugin installed, you can access the activity at the NASA Connect website under Dan's domain. This activity is designed for use by students, teachers, and parents in the school or home setting. Now, you're ready to start the activity. On this site, Norbert and Zod are waiting in an elevator for you to investigate what happens when you accelerate the elevator. If you're the hands-on type and want to try it out on your own first, read the brief directions along the left side of the screen and start by trying to make Norbert and Zod weightless. Then you should read the book on the right side of the screen for important definitions, brief interactivities, explorations you should do, and challenges you should consider. If you want more directions before you start, begin by reading the book, starting with the first page, and click the little right arrow at the top center to go on. To help you get a head start, velocity is the distance traveled divided by the time it takes. If the elevator moves Norbert and Zod downward, we will say their velocity is a positive number. To accelerate is to change the velocity. If you increase the velocity in the downward direction, we will say the acceleration is a positive number. Then, if you increase the velocity in an upward direction, the acceleration will be a negative number. Positive and negative numbers are essential to describe motion. Have fun and explore.
Well, guys, that wraps up another episode of NASA Connect. Got a comment, question, or suggestion? Then email us at connect@lark.nasa.gov or pick up a pen and write us at NASA Connect, NASA Center for Distance Learning, NASA Langley Research Center, Mail Stop 400, Hampton, Virginia 23681. Teachers, if you would like a videotape of this program and the accompanying educator's guide, check out the NASA Connect website. So until next time, stay connected to math, science, technology, and NASA. See you then.
The gravity of the moon. You ready? Yeah. The gravity of the moon.
The young researchers of tomorrow.
Blah, 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 blah.
What?
That's it. Very...
Let me look at it one minute.
Dr. Olson! Jennifer!
Captioning funded by the NAC Foundation of America.